Hey everybody, just going to do a couple of path algorithms for you. We talked about stacks and queues. We did a depth first search and a breadth first search. We talked a little bit about Dijkstra, and we're going to do a couple more path things. They're really important algorithms to know because there's variations of these you can use in a lot of different situations when you're in coding interviews or whether you're just trying to solve a problem. Because what it's going to lead to, well, just the use of the stacks and the queues and priority queues, sometimes maybe a tree here and there. But I'll briefly go over a few of these, and I want to talk about some different algorithmic thinking that you're going to need to understand and some terminology you're going to want to grab onto for your class. So if you take this algorithms class, you're going to hear this terminology, and it'd just be good if you got ahead of it. So and then we'll go to recursion. Right after this, we'll start talking about recursion, and then we'll start talking about merge sorts and different things that binary stuff that we can do with recursion and different searches. So, well, these are like path searches, but different things that we use with recursion. And recursion is important. I don't know why people don't like it. It's pretty simple. All right, let's go through this really quick. So let's talk about shortest path. If you're a game person, we use shortest path a lot, right? You navigate on your phone, you go somewhere that you don't know the directions to. Ideally, it gives you a shortest path. We use wall hacks a lot. Having aimbot do the work that we can be doing. Don't use aimbots. All right. So what are some of the path algorithms? Well, we talked about the depth first search. In the process, you're writing a depth first search. We looked at the breadth first search. In theory, and its ability to find the shortest path in unweighted graphs. This explores all options as it broadens the search. And again, that's unweighted, right? So between the circles, or we call it the nodes, or the vertices, if there's no weight between those, we're just counting the amount of nodes we take to get to a specific spot. Okay, we use this a lot in regular pathfinding. We use it for procedural map generations, flow field pathfinding, distance maps, maps analysis. We use a breadth first search to render landscapes or maps in gaming all the time, right? You finish one area and then you have to jump over a log or open a door or something like that. We destroy that area and we build another area, and we just use a breadth first search from starting one point to build out for you. A lot of sandlot games do that. Minecraft. All right, Dijkstra shows up again. Dijkstra's algorithm, the uniform cost search. This lets us prioritize which path to explore. So instead of exploring all paths equally, it favors the lowest cost, meaning the weights between the vertices. So the weights between the circles or the areas on our graph, we'll say distance to keep it in just our mind. Let's look at this really quick. You're a pen, I hope. Simple graph. All right, so when I say weight, so this is A, B, C, D, E. So A to C is 5 units, 2, and this is 4. So our shortest path, of course, is just go straight A to C, because this way 2 and 4 is too long, right? 2, 3, and 3. And that's also too long. So our shortest path would be straight across. From 0 to 5, of course, we wouldn't want to go around. We'd go this way. So that's what I say when I mean weights. It means that there's something between these vertices, okay? So instead of favoring all the paths, it only favors the lowest cost path, all right? When movement costs vary, we use a Dijkstra instead of a breadth first search. A breadth first search works for an unweighted graph. That's just nodes visited. So we don't have weights between these. We just have what nodes are visited. That would be the breadth first search. But a Dijkstra uses the weights and it favors the lowest cost. Okay? And we have to talk about greedy, because you're going to hear greedy algorithms. And what is a greedy algorithm? So the greedy algorithm, the best first search. Okay? Greedy algorithm is something that we should be familiar with. And what does it mean to be greedy? Well, it means just like a little kid. The greedy algorithm will always make the choice that seems best at that moment. Might not be the most optimal choice, but it's best at that moment. Given two choices, the greedy algorithm, the algorithm will make the best choice at that moment. This means it makes a locally optimal choice in hopes that it'll be a globally optimal solution. Not always, but you got a better chance. Okay? A greedy algorithm makes greedy choices at each step to ensure that the object function is optimized. The greedy algorithm only has one shot to compute the optimal solution, so that it never goes back and never reverses direction. This is all fine and good, but start making with better descriptions, maybe even some code. Okay, let's talk about the greedy algorithm. All right, this is the hello world of greedy algorithms. If you haven't written this, this is something that you should look up or you should write yourself. Find the minimum number of coins. Some of you have done this in problems in earlier classes, I should hope. Okay, you're responsible for making change for a customer, but you want to use the smallest amount of paper and coins possible. Okay, so I buy a taco for 87 cents. I pay with a $10 bill. I want to find what is the least amount of paper and coins that I can get back. Okay, now I could get all my change back in pennies. I get all my change back in nickels and then pennies. And well, that's using the wrong thing because that's not optimal. But we could do it, right? Change is change. So we want to do this. We know what our denominations are, and we're not using a $2 bill, so don't give me that. We know what our denominations are. So we know we paid with a 10, okay, right? Well, we're not going to get back a 10, so what's the one less than 10? It's a 5. So after buying the taco, we have $9.13. Well, a 10 won't go into 9, but the next lowest one is a 5. So a 5 goes into 9, so we're going to use 1 5 because, well, that just cut it right in half, almost. So now we're going to use 1 5. And we can't use a 5 here, and our lowest bill is going to be a 1 because I said no $2 bills. Now we just take 1, 1, 1, 1 until I get done with my ones. Then I'm here. See, greedy. I'm just taking the best solution. What's the best solution at the time? Right? You could write it to just give them dimes and pennies if you wanted to. But that's not optimal. So now I take a 10, and that's 1 dime. And then I can't use a nickel, so I got to go with my pennies. And then I add up every time my iteration hit. 1, 2, 3, 4, 5, 6, 7, 8, 9. A total of 9 combination of dollars or paper and coins. So that's greedy. It made the best choice at the time for the decision it was made. Now, what do I mean? The decision was you have $9.13. Of course, you could use a 1, a dime, a nickel, or pennies, right? But your best choice is to start with a 5, right? That's a greedy algorithm. Is greedy perfect? No. It gets one shot at solving a problem. What it might think is the best solution may not be optimal when the algorithm is done running. This offers some insight on writing greedy algorithms. They're very popular because they're super fast. You usually find a solution based on the information at the time. In shortest path, we can trap a greedy algorithm. And that's pretty cool. So in shortest paths, they can be trapped or confused into thinking they're making the right choice. We can take, if somebody has a greedy algorithm, we can make it really inefficient by trapping it because it's going to make this choice and it might think, hey, I'm going the right way, when really it's not. You can cheat these. That's why we have A star and stuff. All right, this brings us to heuristic versus algorithmic thinking. I'm a heuristic thinker. We write algorithms. So we need to discuss heuristic thinking, okay, and its internal struggle with algorithmic thinking. According to Smart People of Stack Overflow, an algorithm is a clearly defined set of instructions to solve a problem. We know that. What's an algorithm? It's the steps to solve a problem. Heuristic involves utilizing approach of learning and discovery to reach a solution. Okay, so you get to take chances with a heuristic. Maybe it works. Maybe it works in a specific situation, and maybe you like say, hey, this approach works for a specific situation. I'm going to use it for another situation in hopes that it works there too. Right? So you're just taking algorithmic thinking and applying, like, hey, maybe it works. We'll try it. So if you know how to solve a problem, use an algorithm. If you need to develop a solution, it's heuristic. Okay? So greedy algorithm is heuristic. It makes a guess at the time. Heuristics are algorithms, So in a sense, there is none, however, heuristics taking a guess in approach to solving a problem, but it does yield a good enough answer rather than finding the best solution. Sometimes good enough is all we can get. There's algorithms out there that are just good enough. They're not perfect, but they're good enough, right? And good enough is what heuristic approach looks for. So finding the shortest path, greedy best first search. This is a greedy best first search. Many paths are possible from A to B in some graph G. Adding total cost of weights given the path's length. The shortest or optimal path will have the lowest overall cost. Some algorithms to find an optimal path are Dijkstra and breadth first search. Okay? For real applications, we want to compute quickly. Video games, self-driving cars, electricity budgets, routing for internet traffic, things like that. Some algorithms are not efficient. Breadth first search is not efficient. Okay, equal frontier in all directions. Dijkstra only somewhat guides towards the goal. Okay, so they're not really efficient. So let's look at a combination called a greedy best first search. Okay, what does greedy mean for algorithms? Well, we're going to make a choice, and it's going to be our best choice when we make that choice. Okay, this is a heuristic guess at all costs. So I want to go from X to Z. This is my obstacle. These orange ones are just for me to make a point about. These are the only places I can go at the time, right? So how am I going to find the shortest path from X to Z? Well, let's look at that. Let's look at Manhattan distance. City blocks and across, up and across. Okay, so X is here. How far is Z away from X? Right? Well, 7 blocks up. 1, 2, 3, 4, 5, 6, 7, and 2 blocks over. Okay, city blocks. We're 7 blocks up and 2 blocks over. Look at this though. This is a building or construction or whatever you want. So we have to find a path from here to there, and we want it to be the shortest path. So we're going to do this. Like a breadth first search, except our greedy best first is like a breadth first, except you use a queue for ranking using heuristic. We'd use a priority queue for this. Insertion sort, or maybe a heap abstract data type. You can probably get away with a heap, right? Using a priority queue and an insertion sort. The parent in the queue stays so it can backtrack. Okay, kind of like our depth first search. But it stops when the goal state is found. So we're not going to keep exploring like the breadth first search does, where it covers the whole graph. Once we get there, we're done. Fewer nodes are visited than the breadth first search in Dijkstra. It does not guarantee shortest path, and it's vulnerable to maximum traps. And I'll show you what that means. It doesn't guarantee shortest path because it's fully heuristic. So let's look at our distances. So we're going to put weights. We're going to give our distances. So I know this is 7 and 2, 7 to here, and 2 over. So we got to get to 7 and 2. Well, if I go to here, I'm 7 and 3. I'm farther away. If I go here, I'm 6 and 3. I'm 6 and 2. I'm 7 and 1. And I'm 6 and 1. If you're greedy, what's your shortest jump? Right? Well, 6 and 1 is my slowest, but is my easiest. That's the lowest. So greedy, I'm going to take this move. I'm going to 6, 1. That's my lowest jump. All right, now I'm here. Beep, come here, you. So I made this jump. I'm 6, 1. Now I'm going to look at everything that I can go to. Okay. Well, this is 5, 2, 5 up, 2 over, 5 up and 1 over, 5 up and 0 over, 5 up and 1 over, 6 and 0 and 6 and 1. I'm greedy. I go here. Okay. Oh, I want my pen. All right, this is where greedy can make a mistake. So here I am. I'm at 5, 0. What are my weights? Well, I know 5, 1, 5, 1, 4, 1. This is a non-thing because it's a wall, and 4, 1. So here I'm like, oh no, I got to make a choice. Well, let's say I choose wrong. I take this 4, 1. Okay, that's fine. Then I check. 3, 1, 3, 2, 3, 3. Well, it doesn't matter what I choose. Let's say 3, 1. I choose this. I am going to come back to here, and 5, 2 is higher than everything else. I go back to this, kind of like a depth first search. I know I've gone this way. This is called the maximum trap. So I go over to this one. Now I'm right here. Okay. So I check all these out. I can't. I got to go back to 5, 0. That's my open list. I check my 4, 1. The only thing I can do is 3, 1, 2, 1. I get to 1, 1. This is 1, 0, 1, 0, and my shortest path is here. Now I know my shortest path is that. Okay? So you walk backwards through the priority queue to get the path. Good or bad versus a breadth first search? Well, you wasted time in the trap. That's bad. Fewer nodes were investigated. I didn't even bother on this side of the map. You know, all these, no way. Okay, that's good. Breadth first search would have visited nearly every node. Greedy is good. So a best first search, greedy best first search is a pretty cool algorithm to run. Fun to write too. So the greedy best first search, add a heuristic to the breadth first search priority strongly. If it narrows the frontier, it finds the path to the goal in fewer steps. The path may not be the shortest path. Remember, greedy is short-sighted and it's vulnerable to local maxima traps. Just know they're greedy algorithms because your algorithm data structure instructor will say, what's a greedy algorithm? And you can tell them what a greedy algorithm makes the best choice at that time to find an optimal solution, with hopes of an optimal solution. Sorry, with hopes. And no heuristic. Heuristic versus algorithmic thinking. It's going to be on a test from somebody. Not me, I don't like tests. All right, wouldn't it be great to combine both? That's what A-star does. It was developed in '68 to combine heuristic approaches like greedy and formal approaches like Dijkstra. If you just go to 101computing.net and look up Dijkstra's shortest path, this is a great website to take a look at that. You can do that on your own. It's a little unusual in that the heuristic approach gives you an approximate way to solve a problem without guaranteeing you that you get the best answer. However, A-star is built on top of heuristic. Okay, and although heuristic itself does not give you a guarantee, A-star can give you a guaranteed shortest path. Okay, I'm not going to get really mathy. A lot of you guys haven't taken linear or discrete mathematics, so we're just going to leave this here. We've discussed this formula in graphs, and that's one of our last videos. Okay, when to use this heuristic? When we're allowed to move in 8 directions only, similar to King's chess. So go back to 101 computing, go look at A-star search algorithm, okay? And you will find this really easy way to understand the A-star. I'm not going to go, that's their site. You go into their site, do some research. It's fun. Just know that there is a shortest path that guarantees the shortest path, okay? And it's a combination kind of a Dijkstra and my my greedy heuristic algorithm. It's kind of fun. So just go check out 101 computing. And it's when we're allowed to move in 8 directions only, okay? So for great code and explanation of implementation, there's a thing called Red Blog Games, and they have all the code for A-star. So go there. We're not going to type out an A-star. I want to get into, we spend enough time on stacks and queues and these shortest path algorithms. I just want to touch on them so that when you get into your class or you're taking a class and your instructor starts talking about them, you can be like, okay, I have an idea. I'm not coming at this cold. And that's what I want. But I want to get to recursion, and that's going to be the next video. Recursion is awesome. It's fun. And everybody should like recursion because it's just a loop. If you can do a loop, you can do recursion. All right? And thanks to, I borrowed some, these guys, Red Blog Games, pathfinding stuff, and I got some pictures from these guys. All right, you guys are tops. This is a quick little video, but that's all right. It's just, well, one before we tie this one up and go to recursion. We're going to talk about Dijkstra a lot. We're going to come back. We're going to get into graphs, and we're going to talk about different algorithms too, compression algorithms when we get to trees, excuse me, and things like that. All right. I'll see you in the next one. Hope you're enjoying the videos. If so, email me. If not, and there's something you'd rather have me fix about them, email me. I'll make changes. Bye.